This is a lesson in calculus-based mechanics on impulse and momentum, the calculus version. I have already done an algebra-based version of this material. There I talked about starting with Newton's second law. We're using the change in velocity over the change in time to represent acceleration. And we define the momentum, the value for momentum is m times v. It's a vector property. And we see that Newton's second law is a good place to start. And when I did that lesson, we went the simple way through, which was to assume that any external force applied over a period of time on an object is constant. F external is the sum of all forces, and F external is assumed to be a constant value over the time implied. And this was a good place to start with the impulse momentum theorem. It lets us work on problem solving and understanding situations. But introducing the calculus component is going to take us elegantly into another realm of problem solving, and you'll see what I mean here. So how we think about an integral, right? If I start from Newton's second law and I get that impulse is an external force over a change in time, or the differential of the impulse is a force over a period of time, then I can turn that into an integral. If I integrate both sides over the variable time, I have an initial time and a final time, and I'm going to sum up the force over a period of time. And this lets us consider if the force is not constant over a period of time. Of course, if this is a constant, you get F outside the integral, and then you integrate over that period of time, and you just get F delta t. So that's the result, and that's what we use in algebra class or algebra-based version. But here we're going to let the function be vary with time. Okay, so here's a graph over here. I grabbed this from OpenStack's University Physics, Volume 1. And this is a meteor impact force and the average force. All right, so this is the real force here. If I think about a meteor impact, there's a really large strike in the beginning, and then over time it comes to a stop and it stops exerting a force. So over time, this force will vary. And we can represent it with a mathematical function. We could do some curve fitting or whatever and get an equation as a function of time to represent it. If we use the average force, conveniently, it's a good enough approximation, and why we use it is that when we do this integral and assume the average force in that integral, the areas under the curve are the same. And knowing physics, we know that when we take an integral, we're finding the area under the curve. And so that's what we're going to define. That is what the impulse is the area under the curve. Okay, it's related to mass and velocity, but conceptually, that's where we're starting with this. Okay, so we're finding area under the curve. Let's do some problems. That's all I'm going to say about it is we're going to do some integration. We're going to use this tool of calculus in order to help us solve some problems involving areas under curves. And we're going to just look at an area under a curve here. Force on a tennis ball, you can see that the force as a function of time is shown on this graph. All right. Conveniently, there's grids, and we have good solid values here. The graph represents the force on a racket on a tennis ball as a function of time. What is the impulse from 0 to 0.3 seconds? So what I mentioned before is that we're going to find the area under the curve. Okay, and when I look at this, I'm used to doing integrals. This is the integral of a line, and it's a symmetric absolute value upside down here. And I know that if I look at the area here, that area, well, that's a triangle. I know how to find the area of a triangle. Is 1/2 the base times the height. I can do that on here. And I'm going to note that because it's symmetric, the area of the first triangle is going to equal the area of the second triangle. So I'm going to put in a factor of 2. And that's going to be the impulse. That's all I have to do in order to find the impulse here is the area under the curve. So I have values for base and height. The base of this single triangle is 0.15. You all see that. So my factors of 2 cancel. I love when that happens. So I get 0.15, and the height of my triangle is 6 newtons. When I multiply those together, I get 0.9. And what you can do for units here, I mentioned impulse is the change in momentum. We already know that. The impulse is the change in the momentum vector. This is a scalar value. Notice that all of the force is above a positive value. It's above the time axis here. We don't have anything going below to represent a negative impulse. So this is in the positive direction, whatever the positive direction is, and we can consider it a vector. And the units, notice what I did. I took force times seconds, right? So I could do newtons times seconds here, but I'm going to remind you this is also equal to kilograms times meters per second. And those are the preferred units for momentum. And the preferred units for impulse is newtons times seconds. Even though these two are the same thing, they're representing two different concepts. So if you see that any place, do rest assured they're the same value. It's just a matter of preference. The tennis ball has a mass of 60 grams and started from rest. Okay, so I can write things down here. I have an M, 0.06 kilograms. I'm converting to SI when I'm doing this. Notice I want it in kilograms. My units say so. And my initial velocity, words mean things. It starts from rest, so that's 0 meters per second. What is its new velocity? So I'm solving for that. I brought this up here. Impulse is the change in momentum. So I can say I equals mass stays the same, but I have a change in velocity, m delta v. So I'll go m v final minus v initial. I'll solve that for v final. V final equals, let's see, the impulse divided by the mass plus the initial velocity. It's just some quick algebra there. The impulse I calculated is 0.9 over the mass, which is 0.06. And then I'm going to add on the initial velocity, which we know is 0. And when you multiply that through or divide, we're dividing by a fraction, so we're going to get a larger number than the numerator. So 15 meters per second. Okay, so that's how to use a graph to find some impulse. Once you know the impulse, we can do what we know about momentum that we learned in the algebra-based to solve for speed here. So that's a nice little problem thinking about the area under a curve. We didn't actually have to do an integral for that one. We found the area under the curve, which is the concept of an integral. Of course, though, you are in calculus-based physics, so you're going to have to do some calculus here. And so I picked out this graph because it's a very nice function. It's not interestingly curvy in any way, and we can use what we know about calculus in order to lead us through this problem mathematically. It says determine the impulse from 0 to 50 meters per second. Okay, so if I want to do an integral of a force as a function of time, I'm going to write this force as a function of time. And what you see here is that the force is only in the x direction. And so each part of this curve in region 1 and region 2 can be represented by a function f of time, okay? And you're clever here. The easiest one to do is the flat line, where the force is just a constant value. I get 30. No function on time, right? It doesn't depend on time. It's a constant value the whole time. In the first part, I have a line. Okay, well, I can find the equation of a line. I can do the slope, which looks to be 30 over 50, or 3/5, times t with a 0 y-intercept. So I'm not even going to write it in. So that's the force as a function of time for the first region. So I can write that in here, F1, F2. Okay, so let's do some integration. We already know how to integrate these functions. These are pretty easy functions to integrate, but we can go through the practice of integrating a function. Let's see, the impulse, determine the impulse from 0 to 50 meters per second. This is milliseconds. It says m seconds over here, but I interpret it as milliseconds. So I could see a force like when we bounce a ball onto the ground, it's in contact with the floor for milliseconds. So let's do from 0 to 50, and we can see on the graph that's the end of our first region here. Our first force is going to be that 3/5 t, and we're going to integrate that with respect to t. Okay, so let's do our power rule for integration. If this is 1, I'm going to add 1 there and divide by that exponent, so 1 plus 1. So I get 3/10 t squared evaluated from 0 to 50. Okay. So that's just doing the integral, just a quick power rule with the integral, and then evaluating. And we actually have a nice endpoint, 0, if I do 0 squared. So if I do this properly, I get 3/10 50 squared minus 3/10 0 squared. So you can see the last term, that was nice. So 3/5 times 50 squared, when you run this through your calculator, you should get 750. And the units here, we're going to do the same game we did before. We are getting the slope of we're multiplying the base times the height, right? That's what we're doing. So the height is newtons and the base is milliseconds. So we get newtons times milliseconds, and that's fine for that problem. Okay, let's do it again. So that's the impulse for region 1. Let's do the impulse for region 2. I'm going to use this time to conveniently note that in the book that I'm referencing, OpenStax University Physics Volume 1, they use impulse represented with a J. I do not do that. I use it makes sense to me. In physics, we have enough variables that don't make sense. I mean, we're going to use I later for intensity and current, like it comes up a couple of times, but I for impulse makes sense to me. So let's do the second integral. We're going from our two endpoints are 50 to 100 for the next region on our graph. The force function is 30, and we're going to integrate it dt. We can bring 30 outside the integral like I was mentioning for constant force dt, and then we're just going to evaluate 30 t from 50 to 100, and note how that's just 30 delta t. So we get 30 times 50, and you can see this turns into a nice 1500 newtons times milliseconds. So that's the second answer there. Determine the total change in momentum. So the total change in momentum, P net, and we're going to note that I was thinking positive in my head. These are areas above the curve, so I know they're both positive impulse. If we had area below the curve, that would be negative impulse. And so that would, for instance, have a change in velocity, an increase in velocity. Sorry, a negative impulse would decrease your velocity, and here we have a positive, and I'm just adding them together, right? I1 plus I2, I2, these are vectors. I get a plus 750 times 10 to the negative third, plus 1500 times 10 to the negative third, and this gives me, you can see, 2.25 newtons times seconds, or kilograms meters per second. That's what I'm going to put for change in momentum. Okay, I converted back to seconds in order to do this part so that we can get the right units on momentum. So that was a nice little integral. Real sweet. We already know the integral of a line is a parabola, and the integral of a constant function is a line. And so we can find the area under the curve. And it makes sense here that this is half of this area on the graph. So I like problems like that where you can kind of anchor yourself in the math and what you know in order to relate it to what's going on with the physics. And we're getting used to more representing quantities on a graph, right? Impulse, I don't think when you walked into physics, you were thinking I'm going to recognize impulse as represented on a graph, and yet here we are. So let's just keep that in mind. The last problem I have picked out here, hovercrafting on a windy day. I like this one. We're going to do some real calculus here. You can see the force function here is more complicated, dependent on time. It says a 75 kilogram hovercraft going 8 meters per second on a lake receives a force as a function of time from a wind gust modeled with the following equation. So wind gust, this is a wind gust. And when I look at this, and I'll bring this up for you to see, when I graph the function, I get a graph that looks like this. Of course, it's a parabola. And then I was looking at this. I'm like, well, that makes sense that a wind gust kind of starts slow and then it reaches a maximum value and then it kind of dies down, right? So we have that going on for our wind gust. If the hovercraft receives this force in the same dimension as its velocity, and I'm going to notice that this is all a positive value above the time axis, so it should end up going faster, right? If this was negative, like I said, it would decrease the velocity, but here it's all positive, so it will increase the velocity. And what we're going to do is we're going to find the area of this under this parabola, and that will represent the impulse imparted onto the hovercraft. And we also know that impulse represents the change in momentum, which we can relate to the velocity. So that's sort of the big overview of what we're going to do to solve the problem. So the first thing we need to do is find the impulse, and the second thing we'll do is solve the rest of the problem. So let's find the impulse with an integral. We need to do an integral right here, right? We're going to integrate the force as a function of time, dt, and we need our endpoints, t final and t initial. Well, they give us t final and t initial. Notice that we're starting here and here. So that's the practical domain for this wind. I mean, I guess it could have changed direction to the other direction and gone past 10.4, but it's just a wind gust. So we're going to assume it just went back to 0. So we're going to do an integral from 0 to the 10.4 seconds of our function, negative a half t squared plus 5.2t, and all of that goes in front of our dt. So we can do this real slick. We have two power rules. I'm not gonna divide them up into two separate integrals. I'm gonna do them all at once. So what I'm gonna do is integrate this. So this will be 2 plus 1, which is a third. So I get negative 1/6 t cubed. All right, this is a 1 plus a 1, so I'm going to get plus 5.2 divided by 2 t to the first. And I'm going to evaluate all that from 0 to 10.4 when I do it. I'm not going to mess around with writing out the 0. When I plug in 0 in both places here, I get 0 out. So the impulse is going to be negative 1/6 10.4 cubed plus 5.2 times 10.4. And when you run this through your calculator, we're all in the correct units here in terms of seconds, and the force was in newtons, I assume. And so we get 93.739, sort of a palindrome of a number there, newtons times seconds. Okay, so not too bad. This was an easier integral. You can see, of course, how integrals could get harder. If you're in calculus, integrals get harder, but we're just doing a nice little wind gust here with a nice model of a parabola. Nice things is where we start you with integrals in physics. So part B, now that we have the impulse, we can relate it to the the initial and final velocities. We're going to note that the initial velocity is 8 meters per second and the mass is 75 kilograms. And I know the impulse, so the final velocity is going to be I divided by m, just a little bit of algebra here. So I get 93.739 divided by the mass, 75, plus 8. I'm going to note that this fraction is greater than 1, and I'm adding it onto the initial velocity, so that is consistent with what I said, that this wind will speed up the hovercraft, right? And when you multiply that out, you get 9.24985 or something like that. 9.25, 9.3, 9.2, somewhere in there. This problem may look intimidating, but as long as you have calculus as your tool and you have your integration rules nearby or memorized, this isn't a bad problem. We're just finding the area under a parabola.